All right, so today we're going to take a look at some more global limits. And this first example, we want to do it without technology, so we're not looking at a table. Let me just first directly substitute in, and we get 15 over 0, which does not exist. But we would like to be a little bit more specific. We want to figure out if we're talking about positive infinity, negative infinity, or neither. So the only thing we can do is draw a graph. So essentially what this question is asking you to do is sketch a function of this graph so that we can understand which DNE we have. We know that there's a vertical asymptote at x equals 5. We got that from setting the bottom equal to 0. And I'm going to FOIL out the bottom because I like to FOIL the bottom when I'm figuring out my horizontal asymptotes. To figure out the horizontal asymptotes, we're comparing the degree on top to the degree on bottom because the degree on the bottom is bigger because it's degree 2. That means that we have a horizontal asymptote at y equals 0. And now I kind of know the shape of rational functions in general, but in order to make sure that I figure out which parts go where, I'm going to just create a quick table. Whoa, that says f of x. And I'm just going to pick some numbers on either side of 5 to plug in. So let me plug in 6. And if I plug in 6, I get a positive number. If I plug in 4, I get a positive number. So because I'm getting positive numbers above the horizontal asymptote on both sides, I know that my graph roughly looks like this. And once you see the graph, it's a lot easier to conclude that as you're approaching 5 from the left, you're going to positive infinity. From the right, you're going to positive infinity. Therefore, DNE positive infinity. So essentially, you're drawing a graph. All right, so now we're going to talk about N behavior models. So the idea with N behavior models is that you want to find a global limit. A global limit just means that we are heading towards either positive or negative infinity. But we can't really plug in infinity to these functions, and the graphs are kind of complicated. So what we want to do is we want to compare the degrees on the top and the bottom, and we want to just analyze a simplified version of the function. So the reason you're allowed to do that is because ultimately this function has a bunch of crap in the middle, but the N behavior of this function is the same as the N behavior of the simplified function. So what I'm allowed to do essentially is just take the 2x to the 5th and the x to the 5th on the bottom and just analyze what happens as we go to negative infinity of that rational function. Because ultimately that 10x to the 4th doesn't affect the N behavior of the function as much as the 2x to the 5th over x to the 5th does. So I can just look at 2x to the 5th over x to the 5th. Now, instead of plugging in negative infinity directly, we're going to cancel out the x to the 5ths, and now we have the limit of 2 as we head to negative infinity, which is obviously just 2. We couldn't even plug in an infinity, which means that the limit as we go to the right is also 2, which means we have a horizontal asymptote at 2. So the idea here is figure out which term on the top and the bottom is the term with the highest exponent, your degree, and just divide those and plug in infinity. So on this next example, we can look at just our 2x over 3x squared. The 2x is where the degree is on the top, 3x squared where the degree is on the bottom. And I can simplify that by canceling out an x. So I end up with 2 over 3x. And now I have to actually plug in an infinity. So I plug in negative infinity. I get 2 over negative infinity, which is 0. And the reason that that's 0, just as a reminder, in general, if you have a number divided by either infinity, that's always 0. As we go to positive infinity in the other direction, we're just going to plug in positive infinity and get 2 over positive infinity, which means we're just going to get 0. So the horizontal asymptote is at y equals 0. All right, let's look at some more examples of global limits. And again, we're using N behavior models. So if I just do some work off to the side here, I simplify x to the 3rd over 2x squared. I end up with x over 2, which is 1/2 x. So what does 1/2 x look like? 1/2 x is a linear function, and we can see the N behavior. So that means that the behavior of 1/2 x in the long run is the same as the behavior of f of x in the long run. So the limit of f of x as x approaches negative infinity is going to be the same as the limit of 1/2 x as x approaches negative infinity, which is dne negative infinity. And I get the same thing in the other direction when I go to positive infinity. No horizontal asymptotes. You only get a horizontal asymptote if you have a constant as an answer when you go to positive or negative infinity. Okay, now this example D is a little bit more complicated. We have two interesting pieces here. We have a sine of x and we have an exponential function, and we know the basic shapes of those things. We're basically going to use the basic shapes to analyze the end behavior of this function. So let me draw a nice graph. And this is a rough sketch. This is not exact. We want to try to do this without technology. Let's think about what each of these graphs look like and what the range of each of these graphs looks like. So I'm just going to try to color code this a little bit. And this is going to be a little rough, but here's my 2 to the x graph, exponential function. And if I try to draw a sine graph, let's see how this comes out. I'm just going to really ballpark it. Let me switch to yellow. Nope, there's yellow. I got it. Okay, there's my sine graph. Again, really rough sketch. I actually missed the origin. Whoops. It's all good, though. The big idea that I want you to get from this example is that you're adding together these two functions, which means you are stacking their y values. So think about the y values of these two functions. The exponential has really small y values when you're to the left of 0. Throughout the whole domain, the sine function always has y values between -1 and 1. And, once you start increasing your x's, what happens to the exponential y values? They get really, really big. So what we want to do is we want to analyze what's happening to these y values when we consider the fact that we're adding these two functions together. Let's start by thinking about the large y values in positive territory of the domain. If you add really, really large y values to the sine function, which oscillates between -1 and 1, really the -1 and 1 doesn't really matter, right? So technically the exponential function kind of wins out on the right-hand side of the graph. It doesn't really matter that you're adding -1 and 1 to it. Ultimately, the exponential dominates the behavior. But on the left-hand side, the sine function kind of dominates the behavior because -1 and 1 is actually pretty significant compared to the fact that we have a really small y values from the exponential function. So once you come up with a picture of the graph using a rough sketch, you can look at the behavior, and to the left we have dne because it oscillates, to the right we have dne positive infinity, and there are no horizontal asymptotes on this graph. So again, the kind of analysis that I just did there was I'm using the fact that it's a sum between these two pieces, and I'm thinking about the range of each of these pieces and how the y values fluctuate. On the left-hand side of the graph, if you take the sine graph and you just add really small numbers to it, it doesn't really change. That's how I knew that on the left-hand side I basically have the sine function. And on the right-hand side, if you take the exponential function shooting off to infinity and you add -1, 0, and 1 and everything in between, it doesn't really change the exponential function that drastically. So that's how I was able to determine that my graph is going to look something like this. I have some idea of the basic shape. And the values in the middle might not be super accurate, but that doesn't matter because we're trying to figure out the end behavior. That's the whole purpose here, right? We're just trying to figure out what happens as we go to negative infinity and what happens as we go to positive infinity. Ultimately, in the long run to the left, the sine function wins out. It keeps oscillating. It doesn't matter that I'm adding fractional y values to the sine function. And ultimately, as I go to the right forever, the exponential function wins out because a large exponential y value isn't impacted greatly by adding any value between -1 and 1 to it. So that's my logic. Hopefully that makes some sense. Thank you, guys.